Okay, let's get started. So I'm recording this video because we missed a couple of classes because of my business trip and then the national holiday. So okay, let's get started. So in the previous class, we learned about the single cycle processor design, right? And then what is the issue? What is the performance issue in the single cycle processor? So performance, right? Performance issue in single cycle processor. So it is because in a single cycle processor design, the clock period needs to be higher than the accumulation of the delay. And then, so actually, in order to execute an instruction, then we need to use the instruction memory, register file, ALU, and data memory if the instruction is the memory instruction, and then the result needs to be written back to the register file. Okay, so these data path elements have uh, delays, right? Obviously delay because these are hardware circuits and the hardware element. So actually, in order to calculate the critical delay, then we need to we need to add all delays of these circuits, right? So, and then, in order to make the digital system work correctly, the delta t. So this delta t is to be within the TC. So all processing, need to be complete within the 1 clock period, right? So which means, so in order to build the single cycle processor design, the TC needs to be higher than the accumulation of all delays. And then, so TC has a large value. And then, the the performance equation is instruction count multiplied by CPI multiplied by TC. So we know the performance is proportional to the clock period. So this is the performance issue in the single cycle processor, right? So now, we will learn how to improve the performance in CPU using pipelining, okay? So as I mentioned, so this is very important topic in this course. So it means, so you need to understand the concept of pipelining. Also, you need to understand the performance issues. Also, you can observe several performance issues in the pipeline architecture. So you also need to understand the performance issues in the pipeline processor. Okay. Okay. Let's see the analogy of pipelining. So this is very popular analogy. It is because so as I mentioned, our textbook is a very popular textbook, and then many universities use this textbook for learning students, right? And then so actually, so that's why this analogy is very popular, right? This analogy explains the benefit of pipelining. Okay, so as you can see, the title is pipelined laundry. Okay, so I will use the example of laundry process as for explaining the pipelining concept. Okay, so let's see the analogy. Okay, so there are several tasks like A, B, C, D. So you can understand that these tasks are like the clothings, right? And then in order to perform the laundry process for clothings, then let us assume that we have four steps. So these four steps are, we need to use the four steps, four steps. So firstly, we need to use the washing machine, and then we need to use dryer, and then we need to fold the clothings, the folding, and then we can, we need to put the folded clothings to closet. Okay, so closet. So we can say that these are four required steps for laundry process, right? And then also there are multiple tasks. So which means, so we have many clothings, right? So you need to perform the laundry, this laundry process for multiple clothings, the multiple tasks. So, and then let us assume that each step takes 30 minutes, it's a half hour. So in order to complete a single task, task A, then it will take 2 hours, right? So obviously 2 hours because so there are four steps and then every step takes 30 minutes, right? So 2 hours. And then we complete this laundry process for task A. Then we can start the next task, task B. Then it will take also 2 hours, and then task C. Then it will take also 2 hours, 2 hours for the task D. So for these four tasks, then we will take 8 hours, right? And then this is obvious, right? But we can observe also the performance issue. What is the performance issue? So we can say that, oh, this 2 hour. So we need to take 2 hours for a single task. Now we can think that, oh, this is long, right? So it means in the unit time, we can just perform, actually both 8 hours, we can just perform the four tasks only, right? So it's a performance issue. But in this laundry process, so we can also observe some other issues. What's that? It's underutilization. Now, what does that mean? So let's see this laundry process. So for the first step, is the washing machine. Say we use this washing machine device. So you can understand that this is the hardware resource. But out of these 2 hours of overall processing, we just use this washing machine for only 30 minutes. Then what is the utilization of this washing machine? The utilization is 25%. It is because for this 1.5 hour, we do not use washing machine. The washing machine is just wasted. The hardware resource of this washing machine is wasted for 1.5 hour, right? Dryer is the same. So we just the utilization of this dryer is also 25%. Right. So what is the problem? We have resources, but with this simple processing manner, so you can understand that this is similar to the single cycle processor design. So this is analogy is for the single cycle processor, right? So, and then problem is that so we have hardware resources, but the hardware resources are underutilized. So because the laundry process is composed of four steps, and then actually for a single task, we can use only a single step for some a time slot, time window. Okay, so so utilization is low. Okay, this is the problem. So we can perform the laundry task in a pipelining manner. So what is the pipelining manner? So you can observe this analogy. So like the previous example, we have four tasks A, B, C, D, and then also the laundry process is composed of four steps, right? And then firstly, we can use the washing machine, right, for 30 minutes, and then this washing machine is assigned to task A. And then this task A is transferred to the dryer, right? And then we can observe that the washing machine is empty. So what does that mean? This washing machine can receive a new task because this washing machine is empty, right? So, and then also the task A is transferred to the dryer. So we can give new task B to the washing machine, okay? And then after this task B is transferred to the dryer, then we can also give the new task C to the washing machine, okay? So in this example, we can observe that the utilization is higher, right? So for these 2 hours, actually we can always use washing machine. So utilization of washing machine is 100%, right? The hardware resources are not wasted. And then what is the benefit? What is also the benefit? For performing these four tasks, we can take only 3.5 hours, right? So until completing the task D, we just consume 3.5 hours, right? So compared to 8 hours and 3 hours, what is the speed up? Speed up is 8 divided by 3.5, and then it's similar to, it's approximately 2.3, right? So if we use this pipelining manner, then what is the benefit? We can improve the performance, right, for multiple tasks, right? So I just mentioned that for multiple tasks, if we just apply pipelining, we can improve the performance, right? So what does that mean? If we just focus on this single task, and then if we just compare the this completion time of for this task A only, actually the completion time for this task A is the same, right? So so it just it is complete at 8 p.m. It's 8 p.m. It's the same. But what's the benefit? We can just begin the process for task B earlier. It is because the hardware resources for the first step is empty at this time slot, for this time slot. So in this case, we can assign a new task to this empty slot, okay, empty hardware. So the task B can start earlier, right? So if there are multiple tasks, and then if we just apply the pipelining manner like this analogy, then we can improve the performance. So if there are many tasks, so in this example, we just assume that there are 4 tasks, but if there are many tasks, then what is the speed up? So so in the single cycle manner, like is a example, the upper example, this single cycle can receive a new task every 2 hours, right? How about this pipelining manner? If we just apply the pipelining manner, then this system can receive a new task every half hour, right? Then what is the speed up? Speed up is 2 divided by 0.5, so it's 4. So if there are many tasks, right? So this 4 is equivalent to the number of steps. So it's called the stages. So when you build the pipeline steps, then this is called a stage, right? So it's equivalent to the number of stages, right? So we can improve the performance. So if you see this analogy, then which means you can understand that we can also apply a pipelining to a pipelining manner to CPUs, right? Why? CPU also execute an instruction using multiple steps. So in a single cycle process design, we learned that so we can have 5 steps. So these 5 steps are instruction fetch, instruction decoding, execution, memory, and write back, right? And then usually when a CPU executes instructions, there are multiple instructions. So in chapter 2, so this is the high-level language code. And then we learned that when the high-level language code is compiled, many instructions. So many instructions are generated by a compiler. So which means, so we can just understand that these instructions are tasks. It is because a CPU needs to execute multiple instructions and then multiple instructions one by one, right? So multiple instructions or multiple tasks, and then CPU executes instructions using 5 steps, the multiple steps. So it means we can not to improve the performance, we can also apply a pipelining manner to a CPU design. Okay, do you understand? So like this one. Okay, and then also you can understand that actually in real world we frequently employ pipelining, right? So think about the factory. Okay, so you can if you watch TV, then you can observe that in a factory, there is a conveyor belt, and then there are many workers. So each worker performs its own task, right? So its own function, right? Actually function, and then this is the task. And then if this workers complete its function, its job, then for this object, then this object is transferred to the next worker, and then this worker receives the new task, right? New object, actually. So conveyor belt system in a factory is also similar to pipelining. Actually, so in our real world task, we frequently utilize the pipelining. It is because we can improve the performance, right? Right. So it's the same to the CPU design. CPU also needs to execute the multiple instructions, and then and also this in order to execute an instruction, the CPU needs to perform the multiple steps. Right? So for example, we learned that the CPU needs to perform 5 steps of instruction fetch, instruction decoding, execution, memory, and write back, right? Then, let's analyze the performance by pipelining, okay? So this is just the assumption. So let us assume that for register read and then register write, it takes 100 picosecond. And then for other stages such as instruction fetch, execution, and memory, so for each steps takes 200 picosecond. So register read is performed in instruction decoding, and then register write is done in write backstage. Okay, so this is assumption, and then let's compare the required delays. Okay, so load word. This is the load instruction, and right. And then in order to execute an instruction, we need to fetch instruction from the instruction memory. So it will take 200 picosecond, right? And then we need to read register from the register file, right? So it's a load word. Think about the load word x1, and then immediate x2, right? So we need to read operand from the register file, and then also we need to use ALU, and then it will take 200 picosecond, and then memory needs to be accessed using this address, so it will take 200 picosecond. And then for register read, it will take 100 picosecond. So total time for executing a load instruction is 100 picosecond, 800 picosecond, right? 800 picosecond. Stored, the overall process is the same, but the register is not written stored, right? The write back process is there is no write back process for store word, right? So it's 700 picosecond. How about the R format instruction, the R type instruction, like add x1, x2, x3? Instruction fetch is the same, and then register read, ALU, we need to use the ALU, and then it will take 100 picosecond for register write. So total required time for R type instruction is 600 picosecond. Branch 500 picosecond. But in a digital system design, actually we need to use the periodic clock signal. What does that mean? What is the meaning of periodic? So it means the TC is fixed, right? The clock period, we need to use a fixed clock period for clock signal. It means, so that's why the TC, so actually the load word has the longest delay, and then actually the TC needs to be higher than this longest delay, okay, greater than the longest delay, right? So that's why in a single cycle processor design, so in this example, the single cycle processor has the clock period of 800 picosecond, right? And then let us assume that these stages are split into 5 stages, okay? These steps are split into five stages. Then what is the longest delay? So actually, we can just use a single clock period for each stage in a pipeline processor architecture, right? Then what is the longest delay? The longest delay is 200 picosecond, right? 200. So, and then we need to complete this processing within, which means that we need to complete this processing within 200 picosecond, right? Then what is the clock period? Clock period of the pipeline architecture? It's 200 picosecond. So, and then we can just also we can use this performance equation. T the execution time is instruction count, then CPI multiplied by TC. And then actually this instruction count is determined by software. CPI is determined by architecture. But we can assume that TCPI is 1 because uh, I explained. So actually it's not true, but it's just for the ideal processor. CPU can receive every instruction, every clock, right? So we can say that our CPI is 1, okay? And then we can just compare the clock period. So if we apply the clock period, it's because so we just perform this one stage for one clock period. So we can reduce the clock period, right? Because the longest delay is also reduced. It's a 200 picosecond. So by reducing this clock period, we can improve the performance, obviously, right? Right? So this is the example. This is the load instruction, and then in order to perform one load instruction, so that you can find that there are 3 load instructions. So it will take 800 picosecond, 800 picosecond, and another 800 picosecond for the single cycle processor. But if the load instruction is pipelined, so if we use the pipelined processor, then each stage is split, right? Like this. So we can just use 200 picosecond for clock period, right? So no, this is instruction fetch, instruction decoding, and execution, memory, and write back, right? And then another instruction fetch, ID, execution for the next instruction. So, and then you can find that during this second clock cycle, then new instruction can be fetched because this instruction is transferred to the next stage, right? So in this case, the TC, the clock period is 200 picosecond, right? This for the single cycle process design, the clock period is 800 picosecond, right? Then what is the performance speed up? Speed up is 800 picosecond divided by 200 picosecond. It's 4, right? But you can think that why 4? Because in this analogy, then so in this the laundry process analogy, we can observe that the speed up is equivalent to the number of stages. So there are the 4 stages. So the speed up is 4, right? But in this example, in the processor design, speed up is 4, even though we have 5 steps, right? 5 steps for executing instructions. Then why? So it is because the TC, the clock period, is determined by the longest delay, and then longest delay is 200 picosecond, right? So actually, this time for each stage is not balanced. So in this case, then the speed up is less than the number of stages, right? So pipeline speed up, if all stages are balanced, so which means that the delay of all stages are the same, okay, all takes the same time, then the speed up by pipeline is similar to the number of stages. Okay, it's a balanced. If the delay of each step is balanced, right? But if not balanced, the speed up is less. So this is the example, right? It's not balanced, then speed up is less than the number of stages. And then how can we increase, how can we uh, benefit from this speed up? So like, so So you can understand that actually we can improve the throughput, right? Not latency. So actually the latency is the same or the latency can be increased. So think about this example. In order to perform one load instruction, the single cycle processor takes 800 picosecond, right? So which means the latency of a single load instruction is 800 picosecond. But the pipeline architecture, in order to perform the single load instruction, it takes 1000 picosecond, right? So you can think that, oh, the load instruction is complete at this time, but actually, so you know this is the system. Then we need to compute the time using the clock cycle, right? So clock cycle completes at 1000 picosecond, right? So in order to complete one load instruction, then it will take 1000 picosecond. So latency is the same, or the latency can be increased if this pipeline stage is not balanced, right? So latency, we can actually, if we just focus on the latency of a single instruction with a pipelining manner, with a pipelining architecture, we cannot improve the latency. So we cannot reduce the latency of a single instruction, but we can increase the throughput. So which means we can increase the number of instructions per unit time. Okay, so this is called the instruction level parallelism. So it means, so actually, if we just observe uh, this time, we can observe that multiple instructions are executed. So instructions are executed in parallel, right? So this is called the instruction level parallelism. So a pipeline architecture can improve the performance using instruction level parallelism, right? We can increase the number of instructions which are being executed in a processor, right? So it means we can improve the throughput of uh, instructions using the pipelining. Okay. Uh, And then this slide explains that the risk type ISA is good for pipelining design. So it is because, so the risk type ISA is simpler than CISC type ISA. So which means for the instruction decoding, the hardware for instruction decoding can be simpler for risk type ISA compared to the CISC type ISA. The x86 can have 1 to 17 byte per instruction, right? So, and then you can understand that, you need to understand. So, simpler hardware, then we can use less gates, less logic gates. So, which means using a smaller number of logic gates, we can implement the hardware if the hardware is simpler. So what is the benefit? The less gates are used, then delta T is also decreased, the delay. So each logic gate also exhibit delay. And then if we use less logic gates, which means the delay is also decreased, right? So the simpler hardware can, using the simpler hardware, we can improve the performance. But so as I mentioned, the x86 CPU also employ RISC-like architecture. So even though this RISC x86 CPU handles the CISC type instructions, but this architecture is similar to RISC type CPU, right? So that's why the x86 CPU also exhibit a very high performance, right? So, but you can understand simpler hardware includes less number of gates, so we can reduce the delays, right? Okay, so until this slide, I explained about the concept of pipelining. So it's very important. So you need to understand this concept of pipelining. And then, so I believe it's simple. So I believe you can understand, right? So like this analogy, using a pipelining manner, we can improve the performance. And then actually, as I mentioned, in a real world, so we also utilize the pipelining manner, right? I believe you can easily understand the concept of pipelining. Okay. So now, so we will learn about the performance issues of pipelining. So firstly, we will learn about the hazards. So I explained that T execution is instruction count multiplied by CPI and TC. And then, as I mentioned, this instruction count is determined by either software and compiler, right? So this is the software part. CPI is the architecture part. TC is the TC is related to circuit design, right? And then when I explain about the speed up by pipelining, so I assume that the CPI is 1 because we assume a CPU can receive an instruction every clock cycle, right? But actually, it's not. So what does that mean? Uh, the hazard. So read, you can, you need to understand the definition of a hazard. Okay. So what is the hazard in the real world? So actually, hazard is kind of is a flat ground, and then if there is a hole, right, then there is a hole in a flat ground, then when we walk onto this ground, then if there is a hazard, so this is called a hazard, then we can not go through on this hazard, which means we can fall down to this hole, right? So then the the more time will be taken. So actually the meaning of hazard is like this in the real world. So during the flood ground, and then there is some crack or hole, so we cannot go through this path. Okay, so this is the meaning of a hazard in the real world. Then what is the meaning of hazard in the CPU? You can read this sentence. Hazard represent the situation that prevent starting next instruction in the next cycle. So what does that mean? So I explained that we just assume that this is a CPU, and then CPU can receive the next instruction in the next cycle. So which means CPU can execute an instruction every cycle, right? But this is the ideal case. Sometimes CPU cannot receive the next instruction in the next cycle. And then this situation is called a hazard. Okay. So you can understand that a hazard represents the clock if situation that clock cycles are wasted. You can call this situation as hazard, hazard, right? So, uh, so we can calculate the clock cycle for executing an instruction, and then for some situation, then the clock cycles can be wasted. Then you can call this situation as hazard. Okay, clock cycles are wasted, then it's a hazard. Okay, then why hazard are critical for the performance of a CPU design? Because CPI, clock cycles are wasted. What's the definition of a CPI? It's a clock per instruction. And then we assume this is one for the ideal CPU, right? So it means in order to execute an instruction, we just consume one clock cycle. But clock cycles can be wasted. So this number, the CPI, can be larger than one. What's the problem? CPI is increased, then the execution time is proportional to CPI. So CPI is increased, execution time is increased, performance is decreased. So it's critical for the performance, right? And then in a single cycle processor design, we assume that the CPU complete the actually the uh, CPU completes the instruction execution within one clock cycle, right? The CPI is one, but pipeline the design, then CPI can be increased. That's why we need to learn about the performance issues like hazards in a pipeline processor. Okay, and then there are three types of hazard: structure, hazard, and then data hazard, and the control hazard. So we can classify hazard into three types: structure, data, and control based on the reasons of hazard. So structure hazards. So I will explain about the detailed meaning of these three classes of hazard later. But anyway, so structure hazard is caused by the lack of hardware resources. So it means a required resource is busy, then the instruction cannot be given to these hardware components, right? So if the instruction is given to the target hardware component, then clock cycles need to be wasted. So are wasted, right? Because this instruction needs to wait until the target hardware is available, right? So this type of hazard is called the structure hazard, and then data hazard. The need to wait for previous instruction to complete its data read write. So what does it mean? Data hazard is caused by data dependency. Okay. So for example, in order to perform so C equal A plus B, D equal C plus 1. So in order to perform this D, in order to calculate the number D, then actually we need to until the the computation for C is complete, right? So this is kind of a data hazard. And then control hazard. The control hazard represents that the clock cycles are wasted because of control instructions. What are control instructions? Branch, jump, and we did not learn yet the exceptions. Exceptions. Okay? So in a CPU, the clock cycles can be wasted because of the lack of hardware resources. The structure hazard or data dependencies is data hazard, and then because of control instructions, it's control hazard, right? So let's see the detailed situation. So as I mentioned, structure hazards are caused by conflict for use of resources. So it means so this is the hardware resource, hardware components, and then if a certain signal or certain data is given to this hardware, then it will take time, right? Then the until we get the result from this hardware, then it will take time. So which means these hardware resources are occupied. And then while this hardware is occupied, new data cannot be given to this hardware. Right. Okay. But sometimes multiple instructions try to use these hardware resources, but uh, actually, if this hardware resource is occupied by a certain instruction, then other instructions cannot use these hardware resources. Then until this hardware is available, we need to wait. We need to wait. So wait means clock cycles are wasted. So this waste of clock cycles is called a structure hazard, right? It's a structure hazard. So conflict for use of resources. But in our simple CPU design, we cannot find these structure hazard cases. Okay, so this is because we design some hardware resources available for each instruction. So then let's see why. So, when we learned about the single cycle processor design, then we we learned that a single cycle CPU includes the two memories, the instruction memory and data memory, right? But in chapter 2, we learned that actually the instructions and data are stored in the single memory space, right? But when we design a single cycle processor, we split the memory for instruction and then we split the memory to the data memory, right? Then why? Actually, we want to avoid the structure hazard. What does that mean? So let us assume that the instructions and data are stored in the unified memory, like a single memory, right? It's a mem. And then actually, in order to get some data from the memory, we need to give address, and then it's a data. So which means for every instruction, in order to read an instruction from the memory, we need to give address for instruction. Then we can get the instruction. Then how about the load or store instruction? Load or store instruction need to access the memory for data accesses, right? But what's the problem? Within one clock cycle, this instruction memory is already occupied by address, right? So actually load instruction or store instruction cannot access this memory. In order to change this address, then we need to wait one clock and then new address needs to be given to this memory. Right. So this is the example of structure hazard. As you can see, memory resource. The address port of this memory resource is already occupied for instruction. So load and store instruction cannot access this memory. So in order to access this memory, then we need to wait one clock, then clock cycles are wasted. So this is the structure hazard. So in order to avoid this situation, we split the memory into the instruction memory and data memory. So instruction memory is always used for fetching instruction, and then data memory is used for accessing data by load or store instructions. So that's why the memory is split into two parts, right? So actually, these memories are actually cache, not the real memory. real memory. So actually, we will learn about this cache in the next chapter, the chapter 5. But so anyway, in order to access the instruction and data concurrently, so in the same time, we split the instruction memory and we separate the instruction memory and data memory to avoid structure hazard, right? Then and then so by separating the instruction memory and data memory, so we can avoid the structure hazard. So that's why in the CPU, the CPU design in this course, we do not consider about the structure hazard. But in the real CPU design, we can observe frequent structure hazard because some units, some hardware units have a long delay. So it is occupied by the multiple cycles. So, and then while this hardware is occupied, then on it, the other instructions cannot use this hardware component. In this case, though, we need to wait. We need to wait until the target hardware resources are available. Right? But okay, we don't need to consider the structure hazard in this course actually. So data hazard. So as I mentioned, the data hazard is caused by data dependencies. And then as I mentioned, we can frequently observe data dependencies in our application. For example, so C equal A plus B, and then D equal C plus 1, like this. So actually not to perform this statement, the formal statement needs to be complete. Okay. So this is the example, add x19 and then solve x19. So in order to use this value in the x19, the add needs to complete right back to the x19, right? But what's the problem? This write back is performed in the write back stage, and then write back stage is the fifth stage. And then sub instruction needs to read data from the register file in the ID stage, and then ID stage is the second stage. So if we just compare the timing of this write back stage and the the instruction decoding stage, then timing is so the timing is it's not fit, does not fit. Okay, so let's see the example. So add instruction, and then if the sub instruction is immediately executed after the add instruction, what's the problem? The write back stage is here during this clock cycle, and then sub instruction is instruction fetch, instruction decoding, execution, memory, and write back. The sub instruction try to read data from register file during this clock period. Okay, this clock period. But as you can see, the data is not stored in the register file, right? So this is the future, this is the past. So because the data is not stored in the register file, the sub instruction cannot read data from the register file, obviously, right? So how can we handle this situation? We need to delay the execution of sub instruction. So in order to read data from the register file, the sub instruction is delayed by 2 clock cycles. So by doing this, the sub instruction is executed in this point, and then ID stage is here. It's the same time, the clock cycle, the same time slot, right? So, but actually we assume that the data can be forwarded in the register files, and this forwarding is called the internal forwarding. So what does it mean? So during the same time slot, so that is clock cycle, then add is writing data to register file in the write back stage, and then sub is reading data from the instruction decoding. And then, so it's a writing and reading at the same time. So in this case, this written data can be given to the output port of the register file. So this is called the internal forwarding in the register file, right? And then we assume the internal forwarding is supported in the register file. So in this case, in this case, the sub instruction, the ID stage of sub instruction is in the same the timing of the write back stage of this add instruction. So in order to make this timing, uh, the sub instruction needs to be delayed by 2 clocks. So 2 clock cycles need to be wasted. So this is actually the significant the waste of clock cycles, right? Because as I mentioned, we frequently observe data dependencies in our application, right? So this is the very critical the performance issues in the pipeline architecture. But we can handle this performance issue using data forwarding. So data forwarding means that actually, even though the the data is written back in the write back stage, but we already have the result data before the write back stage, right? So in this example, so as you can see, we can get the result of add instruction at this point, right? After the ALU, we can get the result. And then when this result is required, so actually the result of this add instruction is used by ALU for this sub instruction. So which means so actually we require this data at this point, right? So if we just compare the timing of the generation of data and then the, the required the timing of required data, then we can observe that this is future and this is past. So actually in a processor, the processor has the required data. So this data can be delivered, the transferred to the input of ALU. It's possible, right? If we just compare the timing of the generation of data and then the usage of data, the consuming of data, then it it's when it's okay, right? So data can be if the data is delivered to the input of ALU, then we can use this data. Then this technique is called the data forwarding. Okay. So using data forwarding, we can handle the data hazard issue by the data dependencies. But if the former instruction is load instruction, then the data is generated at this point. So if the sub instruction is here, then execution is here. So actually the data is required at this time. So it's not possible. If we just compare the timing, it's not possible. So it means if the former instruction is the load instruction, then the following instruction is to be delayed by 1 clock cycle, right? So this data is forwarded to the input of ALU, right? So this hazard is called the load use data hazard. So because this data hazard is caused by the load instruction, right? So in this case, we cannot avoid the waste of 1 clock cycle. Okay. So then, but we can apply the compiler techniques to avoid the load use data hazard. So this is the example. So compiler technique means that a compiler can reorganize the order of instructions within basic block. So this is this is the basic block BB, the basic block, and then actually if we just maintain the data dependencies between instructions, and then within a basic block, a compiler can reorder the instructions. So this is the example. So when this code is compiled, then this is the compiled code, and then you can find that data dependencies. And then so this is the load, and this is the add instruction. The add instruction received data from the load instruction. So we already know that the load use data hazard is observed between this load word and add instruction, between this load word and add instruction, right? So this is the problem, the performance issues. But by inserting some other instructions between this load word and add, then we can avoid load use data hazard. So in this example, a compiler changed the order of this load instruction. So insert this load word between the load word and add instruction. So you can find that the distance is increased between this load word and add instruction. So by doing this, now we can avoid the load use data hazard, right? And then inside of the basic block, this code will generate the correct result, right? So inside of a basic block, compilers can reorder instructions to avoid data hazard, right? And then control hazard. So control hazard is caused by the control instructions. So this is because, so think about the BQ X1, X2, and target. So actually the PC after this BQ can have two different values, like PC plus 4 or PC plus immediate. Right? This is the target. And then problem is that we use PC in instruction fetch stage, right? It's the very first stage, the first stage of the pipeline architecture. And then, but actually, until the PC is set, we don't know the value of this PC. And then when this PC value is set by BQ, in order to know the correct value of the PC after the BQ, firstly, we need to we need to check the condition. Like this condition is checked by ALU, right? And then after that, then we can know the value, the target PC of the BQ. So until we know the result of comparison by ALU, we don't know the target of PC, the PC value after the BQ. So if the BQ is performed, then the clock cycles are wasted until we know the real value of PC. Okay, I think we know the correct value of PC, then the clock cycles are wasted. So this is called the control hazard, right? And then the control hazard, so this is the example, right? And then control hazard can be handled by branch projection, and then we will learn about the branch projection later. And also, this is another example. Okay, so pipelining summary. Pipelines can improve the performance by increasing instruction throughput. And then I said that this is the instruction level parallelism. Instruction level parallelism. So we can execute multiple instructions in parallel, but this we can the multiple steps. So actually the CPU assigns the multiple instructions to the different steps or different stages. Okay. And then but so by applying the pipelining, we can improve the performance. But because of hazard, the clock cycles are wasted. So using the pipelining, we can reduce the TC, the clock period. But because of this hazard, data dependencies or control, so structure is avoided. But because of hazards, the CPI is increased. Okay, so we need to handle hazard. Okay, we need to handle hazard in the pipeline architecture. So this is very critical actually. So in this example, we learned about in this in the today's class, we learned about the two basic, two important concept. The first concept is pipelining, and then the second concept is the hazard. Okay, you need to understand the hazard, and then there are three types of hazard in a CPU. Okay, okay. So I will stop here, and then please watch this video before the next class. Okay. Okay. Thank you for your attention, and then see you in the next class. 감사합니다.